So today we're going to be doing a review of one-dimensional kinematics. Alright, and so if we were to ask how is a car moving or a rocket or even a rock, kinematics is the way we would describe that because kinematics is the study of motion. And this does not mean the forces because we have yet to cover that. Kinematics only describes how things are moving, okay? So the first thing we have to understand is a frame of reference, and that's because this is how we relate the movement to something. So the official definition is a set of axes to serve as a reference to the position or motion of something. But really, in practice, it's whatever is not moving, and that is a lot simpler to understand. So for example, our typical frame of reference is Earth, because we move in relation to the Earth. However, the difficult part of frames of reference is kind of understanding how they change. So for example, for us, even though normally we're relative to the Earth, let's say we're flying on an airplane. Now airplanes travel really fast, but we don't feel like we're going the 500 some miles that the airplane's going because our frame of reference switches to the airplane. So we are relative to the airplane. So choosing the right frame of reference makes physics problems a lot easier. However, you can pretty much choose whatever frame of reference you want. So the first thing we have to do when defining motion is determine the change in position. And we have two ways of doing so. The first way is distance, all right? And distance is a scalar. And that means that it doesn't have a direction, it just has a magnitude. So for example, if we had a path from A to B, and it took this crazy path, all that matters is the length of the path from point A to point B. So the direction does not matter. However, let's say that instead of distance, we were using displacement. All right, displacement is a vector, all right? And so that means it both has magnitude and direction. Okay, so let's go again and look at our path from A to B. But let's say that we went 10 meters this way and 5 meters this way, all right? So our total distance would be 10 meters plus 5 meters, giving us a distance of 15 meters. However, for displacement, we went back 5 meters. And because displacement involves direction, this would be 10 meters minus 5 meters to give us a displacement of 5 meters. We can use the equation delta x is equal to x minus x naught for our change in position, where delta x is the change in position, x is our final position, and x naught is our way of saying the initial position. So just like we have scalars and vectors for how the position is changing, we have scalars and vectors for how the movement is changing. All right, so we have speed, and this is a scalar. And speed is the change in distance per unit time. Okay? And so we write this out as s, speed, is equal to d, the distance, over delta t, so the change in time. All right? However, we also have a vector, and that is velocity. All right? And velocity is the change in the position's displacement, change in position's displacement per unit time. So per time, I know that sounds a little bit complex, but this basically just means that velocity is equal to delta x over delta t. Now when I say delta t, I mean a change in the time. Most problems will give you a time like 39 seconds. And then you wouldn't need to do the math with delta t. But basically, delta t just means t final minus t initial, so t naught. All right? And so we also know that if velocity is a vector, it needs a direction, okay? And so in one dimensions, this is either going to be a positive or a negative sign. And again, velocity is equal to delta x over delta t. And now we know how to plug delta t in. So we just expanded how to find delta t, and we can do the same for x. All right, because if we go back, we remember how I wrote that delta x is equal to x minus x naught. Same for delta t. Delta t is equal to t minus t naught. So really, velocity is equal to the change in displacement, x minus x naught, over t minus t naught. However, sometimes we don't get the t initial or the t final, and we just get a single number that we can plug in. All right? The important thing is that we can only use the velocity equations when there is no acceleration, all right? Because acceleration is a vector, and it is how fast the velocity is changing. Okay? And so, if it's the rate of change of velocity, we can write it as A, acceleration, is equal to delta V over delta T. So t is the same for time, but v, instead of being the displacement, is now the velocity. All right? And so the unit is going to be meters per second squared. We can expand out our definition of acceleration to account for the velocity by taking the final velocity minus the initial velocity and the final time minus the initial time. A lot of these problems in one-dimensional kinematics involve a final and an initial, all right? Because we're looking at how something changes. So for our velocity and acceleration, if they have the same sign, it speeds up. But if they have different signs, it slows down. So in kinematics, there are 4 equations we can choose from. And I know that these look like a lot different than what we just learned. But let's look at them really closely, and we can see that there are only 4 variables. And most problems will always give us 3. V is our velocity. A is our acceleration. X is our displacement. And t is our time. So as long as we know what the problem gives us, we can solve these equations. All right? And so let's practice using each one. So let's say that we have a boy on roller skates now. He's skating at 17.4 meters per second, and he needs to slow down to 9.11 meters per second. And in this time, he covers 45 meters. So how much time does he need to slow down? So let's write out what we know. We know that his initial speed is 17.4 meters per second. We know that we want his final speed to be 9.11 meters per second. And we know that the distance that he's covered, the displacement, is 45 meters. But we don't know the time it'll take. All right? So now we can figure out what equation to use. And in this case, we will use x, our displacement, is equal to 1/2 v plus v naught t. All right? Because in this equation, we have to choose one that we know what we have. And we have v, we have v naught, and we have t. And we don't have t, but we have x. All right? So let's rearrange and let's solve for t. We got that t is equal to 2x divided by v plus v naught. All right? And so let's plug in. T is equal to 2 times 45 over 17.4 plus 9.11. All right? And so we solve this, and we get that t is equal to 3.39 seconds. So now we're told that we have a ball that's been dropped, and we're asked for the amount of time that it will take to fall 60 meters. All right, and so instead of using x for our displacement, we'll use y. All right, and it's going to be negative 60 meters because it's downwards, it's dropped. Okay, we know that the initial velocity is going to be 0 meters per second because it's dropped. All right, so it's not thrown down. All right, we know that it's accelerating due to the speed of gravity. It's falling, so that's at negative 9.8 meters per second squared. And we do not know the amount of time that will take. All right, so let's choose our kinematic equation. This time we will use y instead of x, but same principle here. Y equals v naught t plus 1/2 at squared. Okay, and again, let's look at the equation. We just have to choose the one where we know each of the variables. Okay, let's rearrange for t squared and get that that is equal to 2y divided by a. All right, and so we get that t on its own is equal to the square root of 2y divided by a. Okay, we get that t is equal to the square root of 2 times negative 60 divided by negative 9.8, and this gives us t is equal to 3.5 seconds. So lastly, we're told that a rocket accelerates from 10 meters per second to 30 meters per second over a distance of 15 meters, and we're asked to find the acceleration. So despite the fact that that's a really slow rocket, let's write out what we know. We know that the starting velocity is 10 meters per second. We know that the final velocity is 30 meters per second, and we know that the displacement is 15 meters, all right? However, we do not know the acceleration. Okay, so let's choose our kinematic equation, and we will use v squared is equal to v naught squared plus 2ax. Okay, so we need to solve for a, so a is equal to v squared minus v naught squared divided by 2x. Okay, let's plug in. A is equal to 30 squared minus 10 squared divided by 2 times 15 to give us an acceleration of 26.7 meters per second squared. So the point of those practice problems is getting into the fact that we must select the right kinematic equation based off of what we know, because there's 4. All right, and so I'm really going to go into detail about that here. So in this problem, we're told that we have a ball thrown up at 35.7 meters per second, and we're asked how long it will take to hit the ground. All right, and so we need to write out what we know. So we know that we have an initial velocity of 35.7 meters per second, and this ball is falling downwards. Therefore, we have the force of gravity accelerating it down. So that's negative 9.8 meters per second squared. And if we are hitting the ground, that means that our displacement will end up being 0. And we will use y, since this problem is a ball going up and down, instead of x for our displacement. All right, and so if we think about these kinematic equations, 2 of them solve for displacement. So immediately we can go and rule out the 2 that don't solve for displacement. Okay, and now we have to look at the variables that we know. Well, we have acceleration, and in one of the kinematic equations, we also have acceleration. And since we don't in the other, we can rule that out. So now we know which kinematic equation to use. So I'm going to go ahead and solve this problem using that equation. So x, or in our case y, equals v naught t plus 1/2 at squared. Okay, and so this problem requires a little bit of algebra to simplify. So if we're solving for t, we can go ahead and plug in 0 for our displacement and set this equal to v naught t plus 1/2 at squared. Okay, and so we want to bring v naught t to this side, so we subtract it. So negative v naught t is equal to 1/2 at squared. Then what we can do is divide both sides by t. So we get that negative v naught is equal to 1/2 at All right, we go down a power because we divided by t. And so then we can rearrange, solve for t, get that t is equal to 2 times negative v naught divided by a. Okay, we changed that 1/2. And then the last thing we have to do is plug in. So let's plug into this equation for t. T is equal to 2 times negative v naught, so negative 35.7. And this is divided by our acceleration, so negative 9.8. And we get our t value of 7.29 seconds. The last thing we have to look at are motion graphs. All right, and these show how two variables are changing over time. And the important thing to understand when looking at motion graphs are the slope and what the area under the graph represents, because these will change for the type of graph that we have. The first type of graph that we have is the displacement time graph. So how the displacement changes as the time changes. Okay, so we know that the slope is equal to the rise over the run. So let's plug in the rise and the run. The rise is our y, so x, and t is the run. And this looks a lot like velocity. So in this case, a displacement versus time graph, the slope is equal to the velocity. The other type of graph that we have is a velocity over time graph. All right, so let's again look at the rise over the run, and we end up with v over t, and that looks like acceleration. So on a velocity over time graph, the slope is equal to acceleration. However, in this case, we also have the area under the graph. And the area under the graph is equal to the displacement. So if we're asked the displacement from a velocity time graph, we just need to look under that line and count the boxes or the units or whatever we need to do to figure out the area under that graph. The last type of graph that we have is an acceleration time graph, so how the acceleration changes over the time. This time, the slope does not really matter. What matters is the area under the graph. All right, and so this case, the area under the graph is the velocity. Okay, so let's refine on this a little bit more. Let's say we had one of those acceleration time graphs. All right, so a, t, okay, and we had a line that looks like this. At this point, it's 7, and at this point, it's 20, okay? And so what we can do is we can figure out the velocity from this. So 20 times 7 divided by 2, and that's going to be equal to 70 meters per second. We just found a velocity from this graph. All right, you can also use a kinematic equation if, finding the area is a bit difficult, where delta V is equal to 1/2 A times delta T. We have to choose the right equation. In this case, it's an acceleration time graph, so we know what A and T are, okay? And so we get that delta V is equal to 1/2 20 times 7, and it's delta T, so T minus T naught. So we would start at 0, so 7 minus 0. And we would also get that V is equal to 70 meters per second. Either way works. And so that is how we interpret a motion graph. And that was our overview of one-dimensional kinematics and the math involved.